Hi everyone, my name is Carly Fox and I'm going to be giving a guest lecture today on categorical variables. So some of you might know that I've been working with Tyson as a part of my teaching product to help develop the flip version of this regression course, and that's been a really great time. So I'm currently a third-year doctoral student in the Disability Disciplines program with an emphasis in speech-language pathology. But my research area is in the development of automated language analysis and also applications of statistical learning and assessment. So I really love statistics and it's a big part of my research. So I hope that you'll enjoy this lecture. Okay, so thus far, and of course, you've only done regressions with numerical variables like age, number of years of education, and so on. But as I'm sure you're aware, in the social sciences field, we often deal with variables that are not numerical or continuous and instead pertain to categories such as disability status or biological sex. And when we use categories as independent variables in regression, we call them categorical predictors. And while we can't treat a categorical predictor the same way as a numerical or continuous one, luckily, they can still be integrated into a regression model pretty simply. The main difference between the interpretation for a categorical predictor is that we want to estimate the difference between means. So, for example, average income difference between men and women instead of a slope, which is what we would do when we have numerical predictors, right? And whether you realize it or not, you've likely done some work with categorical predictors before, probably just under some different names, such as ANCOVA when you have covariates, a t-test if you're using a single two-level variable, or ANOVA if you're using a single variable that has two or more levels. And if you think back to how some of these other methods like ANOVA are plotted, you might remember that when you plot it, you plot the mean value of each group. So again, you could do the mean income of men and the mean income of women. And when you plot a simple regression with a categorical predictor, the plot's going to look pretty similar. So this is what it would look like. So here, we have a regression line that still goes through the conditional mean, just as it has for our other simple and multiple regressions with continuous predictors. But instead here it goes through two discrete points, here and here, right? And so that's the conditional mean for males and the conditional mean for females. And you'll notice that all the points either fall along x equals 0 or x equals 1. And that makes sense, right? Since you couldn't have a value at, say, x equals like 0.05 or 1.7, because we're working with a discrete category that has two levels, male and female. And because we have these discrete levels, we use what is called dummy coding or indicator coding to create an indicator variable in R, because we can't create a regression line from the text male and female. And similarly, we can't just recode male and female as, say, like 0 and 1 or 1 and 2 and treat them as numerical values. And we're going to get more into why we can't do that in just a bit. So we apply these dummy codes to our levels, typically 0s and 1s if you're working with a two-level category, and the interpretation doesn't change much. We're still talking about the effect of a one-unit change in the predictor, such as moving from male to female, but now we're going to talk about that change in terms of mean difference instead of slope. But when we interpret our dummy variables, it's important to keep in mind that there's always going to be what is known as a reference group. When doing this in R, the reference group is always going to be the group that isn't mentioned. So as you can see in this output below, only females are mentioned. So we know that male is our reference group. And when we look at the estimate or the beta coefficient of the dummy variable below, we see that this is the mean difference from our reference group. So we know that negative 0.138 is the mean difference between males and females on some outcome variable. Said another way, on average, females are 0.138 units lower on some measure than males. So now I want you to think on why would we need to have a reference group? Think about that for a moment, and then we're going to return to this point in a few slides. Okay, so now let's look at the interpretation from the perspective of predicted values. So from the output, we get the following equation. Y hat is equal to 0.007 minus 0.138 times our sex variable. So let's go ahead and plug in our dummy code for males, which is 0, and we get y hat is equal to 0.007. And when we plug in our dummy code for females, which is 1, we get y hat is equal to negative 0.131. Sorry. So we know that the mean value for males is 0.007, and for females, it is negative 0.131. So the difference of those means is negative 0.138, meaning that the predicted value of males and females differs by an estimate of negative 0.138. Said another way, females on average are 0.138 units of Y lower than males, just like we talked about before. And just quickly, let's note that in simple regression, the intercept is the predicted value for when the dummy-coded variable is 0, or when, in this case, it's when it's the male group. Okay, so let's return to the point about why we need to have a reference group. So it's important to understand that when you have a two-level categorical variable like biological sex, you only need one dummy-coded variable. If you do make two, this will actually cause an error in R due to what is called a singularity. A singularity occurs when you have perfect collinearity, or you have variables that have a correlation of exactly 1. But why does this happen? Well, it's because if you know someone is female, then by extension, we also know that they are not male. And to include both variables in our regression equation would be redundant because someone being female perfectly correlates with them not being male. So if you included both of these variables in a regression equation, they would be perfectly collinear, and again, that would lead to a singularity. So now we've covered simple regression with a categorical variable. But what about when you want to do a multiple regression? Maybe you want to have a categorical and continuous variable, or two categorical and one continuous, or so on. Any combination of those. But really, any combination is okay. When you have a continuous and a categorical predictor, the dummy variable just changes the intercept. So we can see here that the regression line is higher for females than males. But they're still parallel, right? So the slope is the same. And when you do this with two or more covariates, the line will turn into a plane or hyperplane and so on. So say you're thinking about now standardizing your multiple regressions so that you can remove all your units and then just compare all your variables in terms of standard deviations. Well, it's important to note that you shouldn't standardize your categorical predictors because remember, those dummy codes aren't numerically meaningful. They're essentially just placeholders. So standardizing them can hurt your interpretability. So really, bottom line, just don't do it. Okay, in another situation, maybe you've also thought about or actually tried making a numerical variable categorical so that you could use an ANOVA. So for example, think clinical depression cutoff points, or maybe you had a continuous variable for age and you wanted to split it into a young and old category. But typically doing this is not recommended for a number of reasons. 1, it makes your regression less powerful. In addition, it also throws away information, it treats similar people as though they were different, and it also increases your measurement error. But also, there are some times when this might be justified, such as clinical diagnoses, if you have a variable that is naturally dichotomous, or if you have a really severe bimodal distribution in your data. So what about a categorical variable that has more than 2 categories or levels, such as ethnicity, religion, political affiliation, anything like that? Well, those are called multi-categorical variables, and they can also be represented as a set of dummy variables. So similar to our discussion before, you never want to have the same number of dummy variables as you do categories, as this leads to redundancies and thus collinearity. So instead, you should always have, general rule of thumb, k-1 dummy variables for k levels. So if you had 4 categories, then you should have 3 dummy variables. Pretty simple. And you may also be thinking, what is the difference between linear regression that has 2 or more categories and a one-way ANOVA? Well, really, there isn't much of a difference. It's just that the information is presented slightly differently. So we know that in regression, we do what's called dummy coding, and ANOVA just uses a different type of coding that's called effect coding. Another difference is that ANOVA shows our output in terms of the means of each group, while regression is going to show the mean difference of each group from the reference group, which again is your intercept. But both are going to give you the same F statistic and p-value, so they're both going to lead to the same conclusions. Okay, so let's try an example of dummy coding a multi-categorical variable. So here we have a multi-categorical predictor, marital status, that has 4 levels: married, divorced, single, and widowed. So first, we need to pick a reference group, right? And R is going to do that automatically. It's just going to choose what it deems the lowest value. So here, married is considered the reference group. Then we're going to create 3 variables based on those remaining groups. So that's going to include divorced, single, and widowed. And then say you have an observation for a person that's divorced, for example, then the divorced variable will get a 1 under that category and then a 0 under the single and widowed variables. And if they're not divorced, then they would get a 0. And this is done for each of the 3 dummy variables, and to kind of give you an idea of what that looks like, this is what R is doing on the back end. It does this all automatically. This isn't something you would need to do by hand. But as you can see here, the first 10 observations that are in this box all have zeros for each of these values, and that's because these values represent our reference group, right? They're married individuals. And then once you get past the 10th observation, you look at observation number 11, you can see that there's a 1 under the divorced group, which means that this individual is divorced. And if you go down to observation 21, then you see there's a 1 under single, which means the individual is single. Okay, so not too bad. So now we come back to the question of why we can't just recode our categories with numbers and then treat them as continuous variables. Well, the thing is you could, but then your interpretation wouldn't mean anything. So let's say you replace the marital status levels, married, divorced, single, and widowed, with the values 1 through 4, and you ran the regression. Well, you might get something that looks like this. So you have an estimate of 0.2794 and a p-value that is not statistically significant. Okay, but then let's pretend that you had coded it a different way. Maybe you coded it 4 through 1 instead of 1 through 4. Well, that might result in this output, which as you can see is totally different. In this case, your estimate is negative 0.3364, and your p-value is statistically significant. So these are totally different results that have wildly different interpretations. So in order to ensure that your results are valid, it is critical that you use dummy variables when you're working with categorical variables. Okay, so now we know what not to do. Let's look at what a multi-categorical regression should look like. So we're going to return to our marital status data. And in the table here, you can see that we have our descriptive statistics. Here we have our continuous variables, so those are in terms of means and standard deviations. And then here we have our categorical variable, so it's in terms of counts and frequencies. So now we're going to use a regression to test the equality of the means across our 4 different levels, 1 through 4. And again, this is going to be the same thing as doing an ANOVA. We want to obtain an F statistic that's going to allow us to test the null hypothesis that states that there's no difference between our 4 different groups. Okay, so let's look at our output. So we get an F statistic and a p-value, and we can see our p-value down here is 0.02917. That's less than 0.05. So we can conclude that we're going to reject the null hypothesis. P-value is less than 0.05. We reject the hypothesis that there's no difference across the means, right? Okay, but how do we interpret the regression portion of this output? So this top portion up here, specifically pertaining to the regression coefficients or our estimates. Well, if we plug in each estimate to our regression equation, which is down here, we can compute each group mean, which is these values over here. And so note that we plug in both the estimate, which comes from here, as well as the dummy code. So let's look at married, which is our reference group, right? So we plug in all of our estimates down in the equation, and then you can see for each variable, we plug in a 0, right? Because married is our reference group, so it's essentially just going, or not essentially, it is just our intercept. And then if you go down to divorce, we plug in a 1 for the divorce variable and 0 for the other categories, which will lead to a mean of 79.2 for the divorced group, and so on. Okay, but what happens to that interpretation when we add in a covariate? Well, several things are going to change about our interpretation now because we have this, and that's going to impact our intercept, right? So the intercept is no longer the mean of the reference group. It's the mean of the reference group when the covariate is equal to 0. So it's the mean of married when income is equal to 0. So now each comparison is going to be holding the covariate income constant, and the covariate can also be interpreted as the effect while holding our multi-categorical variable constant, which is marital status, right? So not too bad, but we can't interpret it exactly the same. So how are the coefficients in this model interpreted? So remember that the intercept is now the mean satisfaction of a married individual, which is our reference group, when the covariate income is equal to 0. So the intercept tells us that the average married individual who earns $0 has a mean satisfaction of 53.178. So in order to answer these questions here, such as is divorced, or how satisfied is this someone that is divorced and makes $70,000 a year, we'd need to return to our regression equation, which again we form from our estimates and our dummy codes, and we plug in the values. So you would want to plug in a 1 for divorced and a 70,000 for the income, right? And then you would be able to compute that value. And we're not going to do this here in the video, but it might be worthwhile for you to pause the video and try one or more of these now, or maybe you could come back to it at the end of the video just to make sure that this is all making sense. Okay, so another important piece in interpreting a multiple regression with a categorical variable and a covariate is the adjusted mean. And that is just where the group's conditional mean are at the average of the covariate. So if we look at this plot, we can get each group's adjusted mean by finding the average income line right here, right? And seeing where it intersects with each regression line. So at these points about there. So for widowed, which is coded as 4, it looks like the adjusted mean could be about 75. So on average, a widowed individual making the average income has a satisfaction score of about 75. That's how you would interpret that. Okay, so thus far we've talked about dummy or indicator coding, but it's important to note that there are alternative coding systems. So I mentioned before that ANOVA uses effect coding, and there are even other varieties such as sequential or Helmert coding. But we really don't need to go into them right now. What's important to take away from this is that different coding systems exist, and they will lead to the same overall results, so like the same F statistic and p-value as we saw before, but it will change how the coefficients in the model are interpreted. And there are times when different coding systems are preferable to others. And if you want to read more about that, I've posted some links here. And then there's also an additional link if you want to know about Helmert or sequential coding at the end of the slides. Okay, so a final topic for categorical predictors are contrasts. And a contrast is exactly what it sounds like. It allows you to compare or contrast two or more groups, asking questions like, are two groups different from one another? Or you can ask more complex questions such as, are 3 of the groups in a category different from the remaining 2 groups in a category? So you can make contrasts as simple or as complicated as you want. Okay, so let's try an example. So say we want to know if widowed individuals differ in satisfaction from the other marital status group. So again, that's married, divorced, and single. That's going to be represented mathematically as each of those means divided by 3 minus the mean of our widowed group. And so to calculate this contrast, we then plug in the means for each of these groups. So we're going to be multiplying 1/3 by the mean of the married group, 1/3 by the mean of the divorced group, 1/3 by the mean of the single group, and then subtracting our widowed group. And that will lead to the value of negative 10.867. And that is interpreted as the mean satisfaction of widowed individuals is estimated to be, on average, 10.867 units lower than the average satisfaction of married, divorced, and single individuals. So really the purpose of a contrast is that instead of just knowing that there are significant differences between the means of these groups, it allows us to pinpoint where those differences exist and what they are. And if we want to know whether the contrast we examine is statistically significant, so is the widowed group significantly different from the 3 other marital statuses, we can calculate a t-statistic in a similar way to how we would have done for simple regression. So we're going to calculate the standard error of the contrast and then divide the contrast by that standard error, and that's going to give us our t-statistic. But of course, we would never do this by hand, because we can do it in R. So this is done by assigning our regression to an object, so our regression equation, and here we call it M1. Then we're going to create the contrast matrix, and this is the same one we used in our example. And we're going to assign that to object K. Then we're going to use the GLHT function from the multcomp package. and we're going to run a general linear hypothesis test on our contrast. And that's going to produce this output. And this should look pretty similar to our regression output. We have an estimate, we have a standard error, a t-value, and a p-value. And as we can see here, this contrast is statistically significant. Okay, so I hope you all have found this lecture at least tolerable. If you have any questions, please feel free to reach out to me. Tyson can provide you with my email. I've also listed a few helpful resources if you're still feeling unsure about any of these topics, or if you want a more in-depth explanation of some of the topics that we only briefly touched on. All right, well, thank you so much for your time, guys.